Good morning, everyone. It's great to have this opportunity to describe some of our research with tailings dams, heap leach pads, and other applications for geosynthetics in the mining industry. So there's the title, Geosynthetics and Heap Leaching in Tailings Dams. The outline for the presentation is here. First, talk about heap leach, then tailings, and then I'd like to focus in on the 2015 tailings dam failure and wrap up with a brief summary. Okay, so here's a history of geosynthetics in the mining space, starting in the early 80s with some heap leach pads, all the way down to, say, 2011, and sort of focusing in on the bigger projects. 2011, solar panels being installed on line slopes of tailings piles. So that sort of dovetails with what's happening in, say, reservoirs and floating covers, where solar panels are also being added to those geosynthetic applications. Okay. So here are just two examples, a tailings management facility on the left and a rock cover on a heap leach pad on the right. So the heap leach, we'll do heap leach first and then tailings second. So heap leach provides some very challenging conditions for geosynthetics and geotechnical applications in general. The loading conditions involve both static, seismic, and blasting loads, and you'll see we'll incorporate blasting loads and seismic into our Fundow 2015 analysis. Type of material to be placed on the liner system, not only the composition of it, but angularity of it, and so that'll help us decide about puncture resistance, how it's going to be placed, and then another key is the hydraulic conditions, what solutions are going to be used, because we have to make sure the geosynthetics are chemically compatible with the solutions that are going to be used for the operation. So here's a simple configuration for a heap leach pad. Here we just use a single bottom liner or single geomembrane below the heap leach pad. That's shown right here, and the ore stacked up, irrigation at the top, and the geomembrane at the bottom collects it and is able to take it out to treatment process. So that would be a single liner or single geomembrane system. Other configurations could utilize a double liner or double geomembrane configuration, such as here. We have a heap leach pad over here. There's a single liner system, but where the hydraulics are such that the head will be higher on the geomembrane, maybe that's the area you install a double geomembrane or a double liner system here at the bottom, where the solution will be stored before being removed. And the configuration for a single or double liner system are sort of highlighted here. The single is at the top a prepared foundation or subgrade, a bedding layer to put the geomembrane on. We don't want to lay the geomembrane on a rough or rocky subgrade because that could impact the performance of the geomembrane. And there's the geomembrane right here. The selection of the geomembrane should be driven by the solution being used, the shear strength or interface strength we need for stability, reinforcement. If puncture is a big problem, maybe we need reinforcement in the geomembrane. So a lot of considerations for the geomembrane. So now let's shift to the double geomembrane system. There's the same subgrade bedding layer. So the secondary geomembrane, a leak detection layer in between. So that leak detection layer could be a sand, a gravel, or it could be a geosynthetic drainage composite, and that could consist of a geotextile, a geonet, and a geotextile. I don't know if we brought any samples down with us from yeah, so we'll pass around a drainage composite, but that would be a double-sided drainage composite with a non-woven geotextile, a geonet to convey the liquid, and a second geotextile, and thus a double-sided geocomposite. So the detection zone is very important because that tells us how well the primary geomembrane is operating. The primary geomembrane is right here. And so if there is a defect in the primary geomembrane, then of course we get some leakage into the detection zone, and we can set up what are called action leakage rates for the leak detection zone, and certain activities or operations would trigger depending on the action leakage rate. Okay, so I think that takes care of single and double. Okay, so what does it look like in practice? Here is construction of a single liner system. Here's the foundation preparation on the left, the liner bedding soil coming in next, and the geomembrane deployment coming over top of that. So it's a pretty sequenced operation, very, very efficient. Here's a heap leach pad. Here's the geomembrane being installed. Cushion geotextile here, and of course the ore pile right behind it. Here's the full operation. The ore is being stacked in the back and placed on, notice, steep line slopes, and I'll talk a lot about slope stability in just a minute, but frequently slopes do exceed, say, 3 to 1, and of course when we get steeper slopes we have concerns about slope stability, especially with a lined slope, because we have a geomembrane involved which could have a low interface strength associated with it, or some other geosynthetic. So there's the line slopes, the conveyor bringing the ore to the back, irrigation and solution being added on this segment, and so there's a good picture of the full operation of the heap leach. Okay, one other thing, I mentioned it, puncture resistance. So we are dealing with pretty big rock here, just for scale there, and geosynthetics can be damaged by rocks that size, so we need some protection on the geomembrane. If you look to the right, there's the geomembrane. In this particular case, there's a sand layer approximately 6 inches, so that's, say, 150 millimeters thick, and so if anything rolls off the pile, it doesn't impact the integrity of the geomembrane. You can have different puncture resistance from the geomembranes. A reinforced geomembrane has a good puncture resistance. Rob's going to talk a little bit later about bituminous geomembranes, and those also have a very good puncture resistance if that's the key design function you're looking for. Okay, so here's the whole operation. There's the little containment berm around the side, the geomembrane going into an anchor trench, and the pile coming up on top of it. So that's sort of the bottom liner associated with heap leach. A number of cases will want a cover system over top of the heap leach for a variety of reasons. One, it could be to control the temperature of the process occurring in the heap leach pad, or it could be to reduce infiltration. But here's one where the cover's coming up, and you can see a pretty steep slope for that cover. So in this particular case, the geomembrane was left exposed, not covered, because the slopes are too steep. And if that's going to be the case, of course the geomembrane should be able to withstand exposed conditions. So some geomembranes are better for unexposed versus exposed conditions. So this will be a long-term exposure, so you need a UV-resistant geomembrane for this application. Okay, some of the geosynthetic issues. First, foundation and steep slopes, and I'm really talking about stability, foundation stability and stability of the steep slope that's lined with geosynthetics. High winds, that's a problem. The geosynthetics, especially if the geomembrane is exposed, will have to be ballasted. Thermal expansion and contraction, especially that exposed cover, it'll see high temperature variations, and the geomembrane will shrink and expand with those temperatures. Rock puncture I talked about earlier. Low geosynthetic interface strength. And there's a quite active area of geosynthetics involved with direct shear testing or ring shear testing of geosynthetic interfaces to develop a strength envelope for your slope stability calculations and geopipe compression. Okay. So where are the problems developing? And this can help guide the design and review processes. So this is some data from, actually now it's about 20 years ago. So 3 modes of failure: foundation, low fill, high fill. So if you look at that, and the first time I saw it, I was like, boy, that doesn't really make sense to me, right? I mean, from geotechnical engineering, I would think the high fill would be the case where most of the failures would occur, right? Higher driving force, steeper slope, and so on. But, so it's actually the lower fills. You can see number of events up around 18 to 20 giving problems, okay? Foundation, of course, not too far behind. Okay, so that's a quick look at heap leach pad applications for geosynthetics. Let me shift gears now and talk about tailings dam applications and tailings management areas. So here are a couple pictures of different configurations of the tailings reservoir and dam. So here's the dam. The beach, so to speak, is in the back here, and so you have a lot of liquid coming up in contact with the dam. That has some operational advantages. Obviously, the beach forms in the back, the pipes are in the back, but now you have a saturated condition up around the dam, and that can lead to some lower effective stress and stability problems. In the upper photograph here, the beach is near the dam, and so there's a higher effective stress and better stability associated with that. So tailings dams have become a really interesting topic, and they are becoming very significant structures. So here's a list of the largest dams in the world, right? Earth Dam, what is it? It's a tailings dam. So the largest earth dam in the world, it's not Tarbella Dam or Oroville Dam in California. It's actually a tailings dam in Canada, right? Concrete is Three Gorges. The highest is in Tajikistan, but that's pretty amazing that the tailings dam is actually the largest earth dam. Okay, so everything was kind of going along pretty well in the United States until the Kingston TVA tailings dam failure. And so I'll start with the United States. So lost the tailings impoundment, the dams here, lost it here, and of course the tailings traveled a considerable distance. Luckily no one killed, but a significant environmental impact to the state of Tennessee and the surrounding states. This prompted the U.S. EPA to evaluate tailings dams and tailings ponds. So for coal combustion residuals now, say fly ash, bottom ash, etc., FGD, that all now must be placed on a single composite liner system in the United States. So in other words, all that material is being treated as municipal solid waste. So it has to be on a single composite geomembrane liner system. And I'll talk more about the US EPA and maybe some other regulations that are coming for tailings dams in just a minute. So here are the 3 common modes of raising a tailings dam: the upstream method on the left, downstream, and the centerline method on the right. Upstream's very common because you can just kind of move up the stack, so to speak, move out into the area. So if you did happen to put the beach right at the dam, you now have a pretty good foundation to build up the next upstream lift or segment. If not, you're putting the next lift on some very compressible and weak material. Downstream, this is a good configuration. You're sort of building the section downstream, and it's getting bigger and stronger as it moves downstream. The problem with that is most of the time there's not sufficient space to construct downstream. There's a real tight valley or tight configuration, and so that's a tough one to construct. And finally, is a center line, sort of a hybrid between the two, as you see, a little upstream method, but sort of some support from the prior center line of the prior embankment. Okay, so where are the problems coming from with tailings dams? This is a summary of 228 cases. So frequency of failure on the vertical axis, and you can see different failure modes across the horizontal axis. So if we just go to the main or big ones, so this is about 23% slope instability, 15 overtopping, 15 seismic. There are a couple others. Here's foundation, which you saw in a prior bar chart. So there are really 3 or 4 main causes or failure modes to check when we're looking at tailings dams. Now we can break that up further and look at upstream, downstream failure modes. So this bottom, the upper graph is kind of similar to the last one you saw, but now we can come down to this lower graph. These different colors are different modes of failure and direction. So center line is the blue, the orange is downstream failure, upstream is the gray, and the water retention area is the yellow, and not reported as miscellaneous. So you can see, depending on those modes, here's rotational sliding, or basically slope instability. You can see upstream is a problem, downstream is almost the same amount. So you need to check upstream and downstream stability of the tailing structure. Liquefaction, upstream, foundation, say at the center line. And so this gives you some more insight of which direction the failure mode could develop. Okay, so to wrap up the bottom liner systems for tailings management areas, some of the important things to consider, solution, but down here, harsh conditions, high loads, aggressive solutions, and possibly extreme temperatures depending on what's happening in the process that's occurring. So this is kind of a busy table. The next 3 slides are somewhat busy tables, but bear with me for this. So I recently completed a study for the US EPA. They wanted to know what geosynthetic or non-geosynthetic liner systems are being used for tailings management areas. So it looks like the US EPA is considering requiring some liner system for tailings management areas in the United States. So this would be a really big change for the United States. Right now there's no real regulation on that. So there was a little pushback during this survey that it really isn't needed, but here are the results of it. So this first table is for operating facilities, and I looked at hard rock, or I just put up hard rock tailings impoundments. Okay, so this is what's operating. So the box with the red dash over here summarizes the liner systems currently being used in the US for hard rock. So you can see, first one's a double liner, 2 60 mil HDPE geomembranes. Next one's a single liner, but it's 100 mil HDPE instead of 60 mil. So a little better puncture there. Single liner with 60 mil. Now this is just a compacted soil liner. A recent court ruling in the United States for coal combustion residuals ruled that a compacted soil liner does not count as a liner. So coal combustion residuals looks like they'll have to at least have one geomembrane. A compacted soil liner won't do it. And I think that's going to filter over to tailings management areas coming out from the CCRs. Okay, next up is a 12-inch amended clay layer with 5% bentonite and a PVC geomembrane, 30 mil, and then finally a 30 mil LL or VLDPE. So that's what we have as the current operating liner systems for tailing management areas. So the next 2 slides are proposed. So notice proposed hard rock tailings, and the red box on this slide and the next slide show you what mining companies are proposing in the hopes of getting ahead of what might be coming down the road from US EPA. So notice most of it is single. As I talked about earlier, single, 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 single. But notice here's one proposed coming in with a double composite liner system, 260 mil HDPE geomembranes with a GCL underneath the primary geomembrane. So a lot of variability being proposed, but a liner system now being considered for tailing management areas. And I think that's pretty significant because the tailings management areas usually cover a very large area, and so to line that is going to be a significant effort. All right, so this is table part 1. Here's part 2, double. Now, notice this one, natural clay or natural soil, compacted soil liner. Again, this CCR ruling is a federal ruling coming out. It happened in, say, the last 8 months. So I'm not sure this one's going to stay there. I think that's going to convert to a geomembrane, some kind of either a single or double. But there's a double, single. Now this is a composite liner system where you have a compacted soil liner underneath an 80 mil HDPE geomembrane, very similar to what we do with MSW landfills. 80 mil and natural clay. That particular site is just really natural clay. It wasn't a compacted soil liner. They just placed the tailings area, management area in a part of the site where it was underlain by a fine-grained soil. So it's not a engineered material. And then finally, a single HDPE.